Good morning, everybody. Well, morning for you. As you can see, it's turning evening here where I am, which is in pretend San Francisco. Just thought it'd be nice to have a different type of background today. Yeah, it's kind of romantic, I think. Nice, cool evening here in San Francisco. Um, anyway, hope you're doing well. We're making our way through. Oh, yes, I will. Sorry, I will do the transcription. I hope that I got to figure out a way of doing that automatically. Thank you for reminding me. Anyway, making our way through some kind of dense material now. And I realize that the course is getting a little bit, I guess, more philosophical in some ways, more conceptual, theoretical. And so we're going to, take our time and work our way through these things. Hopefully you had a good time yesterday in discussion section getting through some of these topics as well. But what I'd like to do, let me see if there's any quick questions. And then what I'd like to do is actually go through the practice polling question that we did at the end of last class, because we had to go through that quickly. But let's see, any questions? Oh, people are just being friendly. Okay, Erica asked, good morning, Professor. My husband goes to Arizona State and part of his module was to watch this video on mouth noises. He was like, oh, look, UCR, and it was me. It was a BBC video, I believe. Yeah. Yeah, there's a kind of viral video. I don't know if it's still viral, but it's got like 5 million views of the close-up of my face, which is like not something I was ever hoping for in my career. But it was something that I helped the BBC with concerning a phenomena that was related to research called the McGurk effect, which we'll learn about later on in the quarter. Yeah, you'd be amazed at how frequently people come up to me in places saying, aren't you the guy that says ba and va? Yeah, that's me. So yes, well, I hope he enjoyed it, Erica, because I don't. Anyway, yeah, that's me, Sarah. That's me. We'll see more of it. I'll maybe we'll look at it when we get to that topic later on in the quarter. Anyway, all right. Yeah, great. Okay, then let's go ahead and do our polling question. That was, let's see here, the Turing machine, right? Yes. Okay, I'm going to launch this. You don't need to answer it again, but this is the only way I can get you to see it, I believe. I'll just launch it and then I'll stop quickly and then we'll just look at it here. There we go. End poll, share results, no results. Okay. The correct answer for this one, however, was in fact C. Let's go ahead and go through the question a little bit. One important aspect of the Turing machine principle is that, okay, so this is the idea that Turing proposed, just to remind you from your slide, that a system that has a binary code and can kind of control itself can basically perform any rule-based process at all. And that turns out to be very profound when it comes to, our understanding of how perception or cognition or any sort of psychological process works. And so the important components of that idea of a Turing machine is that, yes, it was based on a binary process. It was an automatic kind of self-controlling device. Importantly, as we'll see, it is based on a representational code, which means like the same thing for a mathematical, equation, that the symbols that are used, the numbers in mathematics, the binary patterns that are in the Turing machine can stand for anything. So as far as the actual machine is concerned, it doesn't really know or really care what those codes stand for. And that's an important component, as we'll see. So it's a formal automatic formal system, as we discussed. And then we went on a little bit further and talked about the fact that the Turing machine can be instantiated in a number of different sorts of substrates. So what I mean by that is that the type of material that can support Turing machine types of processes can be, yes, a magnetic tape like Turing had envisioned it, or a computer like you're using now, that's based on silicon switches, as tiny little electrical switches. As long as it's on-off sort of pattern, it can, kind of support this binary code. It's a substrate that can support this binary code. And we of course, then move to the fact that, well, in some understandings, the nervous system is like that, isn't it? It's made up of these, little units, these cells that can be in on and off states, and patterns of on and off states, and therefore it also has the potential to be a Turing machine in the sense that it can support a binary code that can represent pretty much anything, and control itself and be formal, as I said. And so this is a kind of logic that allows us to arrive at the idea that we can understand the processes of the mind, the processes of the brain, by understanding how a machine, a computer, would perform these sort of processes. Okay, and so that's a profound idea. I mean, we're going through this to understand why people, why science that studies cognition, why science that studies psychology can talk about process and can talk about there being some way of understanding mental process by looking at how a computer, or how something like a computer, can perform these things. Okay. Now, of course, you did talk a little bit about, possible differences between computers and people when it comes to these sorts of processes. I assume yesterday when you went through the Turing test and all that cool stuff. We will get a little bit into that ourselves today. But the background is there to at least make the logical proposal that you can understand any sort of complex process as being supported by binary code system, on-off switches, and that's holds for the computers, the magnetic tape that Turing had proposed, and importantly, humans, if in fact our nervous system works that way. So now, armed with those ideas, it's kind of a little review of the last slide. We can go through this question. One important aspect of the Turing machine principle is perception can occur without representations. That's not true. Based on the Turing machine, we're talking about very clear representations in the codes, right? I mean, it can, represent a number of different things, but we're dealing with manipulations of something that is representing whatever it is out in the world. So representations are an essential part of the Turing machine process. So that's not correct. Perceptual organization occurs spontaneously. Hopefully you recognized that answer B is really an idea associated with the Gestalt approach, not this new computational approach that we're talking about. What about C? Any rule-based process can be modeled as an automatic formal system. That, in fact, as I just mentioned, is the point of the Turing system, of the Turing machine system, right? If it's a rule-based process like the Ponzo illusion, or any other sort of perceptual process, any sort of, in some ways, mental process, if it can be discussed as kind of a rule-based system that it kind of goes through a series of steps that can be considered rules, then yeah, it can be modeled on an automatic formal system. That was Turing's point in that argument. And then, of course, that makes D incorrect. Perception cannot be modeled on computers. No. The idea of the Turing machine is that, yes, it absolutely can legitimately be modeled on computers, because computers, like nervous systems, can support the binary code that allows it to go through to solve any rule-based process. That's a good sentence, or it's a long sentence, but it's a good thought. That because perception involves a rule-based system, and rule-based systems can be solved with a binary code. Yeah, whether you're a computer or a person, and you have a binary code basis, whether it's silicon switches or neurons, then yeah, it's the same type of process, essentially. Okay, cool. All right, so I thought it would be important to go through that because there's two reasons. First of all, there's absolutely going to be a question on your exam, right? There you are. There is your question, right? So it's important to understand. But secondly, we're getting, there's going to be more questions like this. And I know these are much more challenging than the ones that we started off with. But, it's important that we kind of think more kind of globally, kind of think thoroughly, and kind of integrate our ideas here. And that's why I thought it'd be important to go through this type of question, since there'll be more of this as we go through. Okay, any questions on that at all before we continue? Cool. I can link the video for those who want to see. Oh, okay. People are still talking about my 15 seconds of fame. That's okay if it makes you happy. I'll show the video later, I promise, if you're really, really excited about that. Okay. All right, then let's continue talking about things that have nothing to do with a close-up of my face, which is, of course, where is the, hold on. Yeah. So here is, in fact, the slide that I just went through, essentially. There we go. And we just talked about all these ideas. Except for the Tinker Toy computer, which is just a kind of demonstration that any sort of system that can, kind of support a binary code, and you can kind of build this with that little toy Tinker Toy set that I grew up with, just these wooden spools and rods, and here's strings that they added to it, that it can in fact play tic-tac-toe, which is based on a process, as you know, of kind of trying to outwit your partner by kind of anticipating different types of things that might happen in the game, and how to kind of control those different steps. Okay, it can be modeled on a Tinker Toy set if you wanted to, but the point is, it is like the computer or nervous system, a binary system that can solve complex processes. Cool. Okay. Armed with this, we're going to come back to this. We're absolutely going to come back to this. But what I'd like to do is actually now talk a little bit about one example of how perception might be solved from this kind of computational perspective. And it turns out to be a very important part of the history of perception, as well as the history of engineering, as you'll see, for those of you that might be interested in that type of thing. And it's the concept of pattern recognition. And the very simple idea of pattern recognition is, how do we recognize patterns of stimuli in the world? How do we know what pattern we're experiencing, whether it's a visual pattern or an auditory pattern, for that matter? You're recognizing the pattern of my voice and the pattern of the speech, but we'll be talking about it mostly with regard to vision. And there's a pattern right there. The letter R is a pattern, and the question is, how did you just recognize that that's a letter R, or how would we get a machine to recognize that that's a letter R? Remember, we are now armed with the concept that by maybe understanding how the machine does it, or how it has trouble doing it in certain cases, we can understand something about human perception. Okay, how might it be done? Well, the way it's often done with a computer, like whether you're scanning, I don't know if you have to do much optical character recognition, but the idea that if you want to scan a paper and then get your computer to kind of make sense of what the text is, so you actually have a kind of changeable and editable text that you've just scanned in your scanner, you have to have your computer recognize those letters, right? And this is the process that it does it by, basically. And also, the pattern recognition of letters and numbers is something that occurs in the post office. Your post office will scan your envelopes and look at the zip code and help sort the mail based on the zip code and all that sort of thing. How is it done? Well, it's done through a process called feature analysis, where it takes the pattern as input and then tries to look for individual features of that pattern. Basically, it's going to be kind of a way of defining what the structure is of the pattern in terms of its individual features. Should sound a little familiar, right? When we talk about kind of the components, the elements, the atomisms of a stimulus, right? It's very similar to what Wundt was interested in with regard to structuralism. So let's go back to our letter R up here. If Wundt asked you in one of his experiments, what are you looking at? And you said an R, he goes, sorry, that's a stimulus error. What are you really experiencing? You say, oh, okay. I'm seeing a vertical line here, I guess, and some little tails on the end of the vertical line. I see a slanted line, a semicircle. You get the idea. And Wundt's going, excellent. Okay, this is exactly what we're after. And this is, in fact, one way a computer, whether it's analyzing the text you just scanned or looking at zip codes on an envelope, can perform this task successfully. So basically, it's going to, another term that you might encounter in this context is a structural description. It's nothing fancy. It's just saying that, basically it's going to do a piece-by-piece description of the structure, essentially. Not verbal description, but understanding what the features are. It's just determining, what each of these individual features are at different levels, and then trying to come up with what the ultimate pattern is that you're looking at. So let's go ahead and do that, right? This is kind of this structuralist sort of perspective where we're doing what Wundt's wanting us to do. We're looking at the pattern that's coming in, this letter R, and now describing its features in the structure. There we go. Make it very clear for us. The features are, of course, as I mentioned, a vertical line, a semicircle, right? Yeah, that's not bad. I guess we can say it's a semicircle, a semi-oval. Yeah, you get the idea. What else do we see? A slanted line. Cool. That's this one right here. And finally, right angles. So now this is now kind of taking a step back, because now we're just not going through the individual features, but actually talking about how the features might interact a little bit. And that's still kind of what Wundt was happy with. We're still not saying it's the letter R. We're saying, okay, I've identified the individual features, but now I'm going to say how the features are related to each other. It's like saying when we look at an apple that the little line on top is on top of the circle, right? And now we're saying that the semicircle kind of connects to that vertical line, and in doing so makes these kind of right angles. Okay. I mean, there's so many different ways you could do this, but this is a good start, I would say, right? Okay, cool. So now, how does this work? The idea would be that there would be some sort of units in the device, whether it's looking for zip codes at the post office or doing optical scanning on your computer and your scanner. It's going to have units that are going to represent these different features. Okay. And then depending on whether those units are activated, whether those units are activated by, the presence of their associated feature in the image, okay, then that information can be kind of kicked up to another level of analysis. So let's go ahead and get some of this in, right? Oh, shoot. Okay, I'm having trouble seeing this because something's covering this up here. Okay, there we go. Let's do it this way. Okay, so the transcript's covering up for me, but the transcription is covering up for me, but hopefully you can see it fine. All right, so along the bottom row here, we have these little, we'll call these little units that are inside the system. And these units are going to represent things that might be in the input stimulus. Let's talk about the device in the post office that's going to look at your handwritten zip codes on your envelope. Okay, so you're sending a thank you letter to your grandma for the $5 she sent on your birthday, right? Which is polite for you to do. You should always do that. And you hand wrote it because she doesn't like when you do that silly thing on the computer. She doesn't like the email, whatever. I'm sure your grandma is much more sophisticated than I am. But let's pretend that she really likes letters. So you go ahead and you not only write a real, piece of mail, because she loves getting those, you hand write the envelope. And so you've handwritten the zip code on the front of the envelope. The question is, can a computer recognize what you've written, even though it's your handwriting and not your friend's handwriting? And hopefully you can take care of all that sort of stuff. So what that machine's going to do is look through, what looks like a zip code somewhere on the envelope, and then go through the numbers individually and look for features. And inside the machine, there's going to be units that are looking for features that might be part of the numbers, but the same thing could be true of letters as well. Since we're coming here and coming back to the slide, talking about letters, there's going to be little units that are inside the device that are going to, kind of become active if they see, the units see itself basically in the stimulus. Okay, so say there's a unit representing a vertical line. If that unit is in fact, if there's an input of a vertical line that comes to the system, that unit will become active. It's as if it's kind of giving it a personality here. That unit's saying, oh, wow, good, excellent. I see in the input me. I see something that resembles me. So I'm going to be active and make lots of noise and saying, good news, everybody. I see myself in the input. Okay. Just to make it kind of intuitive for you. Same thing with the unit next door, which represents a curved semicircle here. That unit says, oh, look, I see myself there too. And so I'm excited because it could be that, or it's the case that there's whatever's coming in right now, a letter, has a feature in it that I represent, which is great news. And I will tell everybody that great news. Hey, everybody, I see myself too. Okay. And of course, my neighbor here, so this is me. Okay. The neighbor here says the same thing, right? Because it sees itself in the stimulus, right? It sees that slanted line and says, hey, me too. I'm making noise because I'm excited. I see myself in the stimulus, and it makes me happy, makes me feel important. Sadly, the neighbor on the other side doesn't see itself, right? Because it's a slanted line unit, but it's a slanted line that goes in the other direction. So this unit goes, oh, well, I'm quiet on this one. You guys have a good time. Hopefully next time I'll see myself. Cool. Okay. So now these units are in fact excited, and they are going to pass their excitement up to another level of units that are going to represent letters in this case. Okay, it doesn't have, we can do the same thing with regard to numbers if we're talking about zip codes, and then if we're talking about fancy pants stimuli, including faces, right? We can have these things represent all the millions of faces that we've encountered in our lives potentially, right? So this isn't just for letters, but trying to make it as simple to understand as possible. Okay, so basically now these units start getting excited depending on which units below have been excited. So P has been told that one of its associated features, that semicircle, is in fact excited and is really, telling everybody that it sees itself in the input. And so is the same thing as me with the vertical line unit. I'm telling P, yeah, that's good news for you, because it could be seeing that we could be looking at a P right now. It's like, great, I'm going to get excited too. I'm going to tell everybody, hey, I've seen both of my important features. It could be me. But look at R. R is getting more than that. R is getting the semicircle. It's getting the vertical line. It's getting its slanted line. And R is saying, oh, now this is great, because I mean, I know P's doing well because it sees both of its features in the stimulus, but I've got more features. I've got that vertical line too, and I see all three of mine. So it could very well be me. K, on the other hand, is doing okay, but not as well as R and P, because K sees the vertical line, cool, and it sees its slanted line, cool, but it doesn't see, it's getting information that that orientation, slanted line, is in fact not being activated. So I say, it's probably not. Oh, and also look at this. That semicircle is there potentially. I'll get this information that semicircle is there. And, I thought I was doing well, but I'm not doing as well as R or P for that matter. So now what happens? Well, K has some activation because there are some features. P has activation because it has both of its features, but boy, R has all three of its features. It has more features than P, and if it's all three of its features, it's getting really excited. And it passes that information up to a final unit, a unit that makes a decision. Okay, he's smiling, he's happy. He's this decision unit. Okay. And he or she looks down at the, or they looks down at the letter units below and makes the decision of which of these letter units is the one that's most active. And based on that relative activity from these letter units, will make the final decision about which letter the system's looking at. Okay, so it says, yeah, there's a little activity from K and more activity from P, but boy, R seems really, really excited. We must be looking at an R. Okay, very simple system. There's lots of ways of modifying it, but it is conceptually the sort of way your zip code reading machine works at the post office. It is how optical character recognition happens to a large degree, right? And it's just a very, very efficient way of going through the process, right? Because, think about this. Your handwritten letters and numbers are different from my handwritten letters and numbers. And so there has to be some level of flexibility, right? So depending on how you write your R or how I write my R, there might not be as much of a semicircle in yours as mine. If you're writing yours cursive, the vertical line might not be there as much. So there has to be some flexibility. The way I've kind of portrayed these features, that these are a very limited number of features. There's going to be many, many, many more features here, of course. And these feature units are going to represent not just individual features. It's also going to represent, the interaction of these features, whether they meet at right angles and everything. So that's fine. But doing it this way is a little bit more powerful. It's more flexible than trying to just match letters directly. Let me just take a little aside here. Before we had this sort of system in machines, in zip code reading machines and optical character recognition and all that sort of stuff, we were able to recognize things like numbers and letters. And a good example for that was the check reading machine. Okay, so this is still how it works. When you, you folks don't even use checks. Okay, no, you do. Okay, so here's how it works. I don't even know exactly how it works, but how yours says, okay, so you take pictures of your checks, right? So my son is my 20-year-old son has never actually gone to the bank. Okay, that's fine. And the way he deposits his checks is by taking pictures of his checks. All right. Well, you've seen checks before, of course, and you know that the bottom row, the numbers at the bottom of your check represent your account, or the account from which the checks have been written, right? What bank and all that sort of stuff. Okay. Next time you get a check, look at those bottom numbers and you'll see they're very, very standard and very kind of quirky, right? They've been created to be very distinct from each other and very regular from check to check, right? So those numbers are the same from check to check. They are not handwritten. They don't have that sort of, flexibility. They don't require that sort of flexibility in a machine to read those numbers that handwritten numbers do, right? And that's how it always used to work, that if a machine was going to be able to interpret numbers optically, those numbers had to be very, very standard, and they had to be very distinct from each other. Okay. But that was because before we had this sort of flexibility in feature analysis in the machine, it was just looking for specific shapes, very specific shapes, and didn't have flexibility. You could not, for example, in an old check reading machine, write those numbers at the bottom of the check in yourself. It had to be machine generated so it could be machine read. Not anymore. We can be much more flexible. So anyway, I was going to say, when my son takes a picture of his check and the bank can interpret all the bank information from that, it's using these very kind of standard computer generated numbers to do it. But these days it wouldn't need to, potentially, because it could use this more flexible feature analysis sort of model. Okay, so it does have that flexibility. What is evidence for feature detection? Well, as I said, I'm just using the term perceptron here. You should know the term. It's just the name of the general sort of model that is used in the post office to read checks in optical character recognition. It's any sort of device that uses feature detection in order to recognize the patterns on an image. That's it. It's just a kind of generic name that your zip code reading machine uses the perceptron model. Your optical character recognition process on your computer that can interpret scanned images will in fact be using a perceptron model. That's all. So it works. It's evidence because it works in these devices pretty darn well. Yeah, sometimes the scanning in the post office isn't absolutely correct. There's always aberrations where somebody writes their, sevens very odd, in the old school way with a line through it or something like that. But for the most part, it does a really, really amazing job. It's successful. Okay. And as I said, it can have this flexibility. So here's all of these different examples of R. I might be very, very kind of square in my style R, and you might be very kind of stylish in your letter R. And yeah, when you look at the feature by feature, you can see that there are differences, but they're going to be, when you kind of include lots and lots of different feature units, they're going to be things that are going to be similar. So there is this semicircle on top for both, and there is this kind of slanted line for both. But if you're including lots of different units for lots of different features, it does have this flexibility, and that's what a perceptron can, in fact, recognize all these things as the letter R. It's effective in that sense. So cool. Maybe, in fact, not only can machines work this way, maybe our visual system can work this way too. And evidence for that, you've already seen some. That single cell stuff, right? That Ubel and Weasel stuff that we talked about last class. One of the kind of pieces of evidence that was used to talk about the importance of features now, right? So remember, we discussed kind of the Gestalt approach being important in some ways, but then this new evidence kind of emerged along with the computer revolution to suggest that features themselves, specific features themselves, are actually really important. And in fact, there seem to be cells in the brain that respond to specific features. So maybe these cells, these single cell recorded cells that respond to either a horizontal line or a slanted line or a vertical line, okay? Maybe those are like those units that you saw on the previous slide. Here's, I've been calling them units just because I wanted to be, general enough to allow the system to be in a device in the post office or in a brain. But this might be what we're talking about. The units here, according to this research, are in individual cells that can detect these individual lines at different orientations, okay? So it could very well be that by understanding how we could write programs to recognize patterns in machines, we can understand how the brain recognizes patterns too, okay? This is classic kind of idea of the Turing machine, kind of this notion that as long as there's kind of, a binary sort of on off, is the cell on or off? Is it recognizing itself in the stimulus? Whether it's in the perceptron, in the post office, or in our brains, okay? Could be the same process, right? Cool. Good. Let's take our little break here and do a very, now I think, simple question, practice question. It's going to be exactly on what we just discussed. But I can take any questions you might have in chat. Let's see. Nope, nothing new there. Before we go ahead. All right. Okay, then let's go ahead and do one of our class questions. This is going to be very simple for you because we just went through it. Oh, okay. I should say something about here. Yeah. Again, this issue with distractors. Eventually, before you take the test, you're going to recognize these distractors. You're not going to recognize them right now. You'll recognize one of them, but don't be intimidated by not knowing these terms yet. You will know these terms in the next week or so. All right, but pattern recognition. I'll read it first and then we'll post it and see how you do. The process by which patterns are recognized through detection of simple components is called, it's too easy, but you get a free question. Is it affordances, emergent properties, feature analysis, or Gestalt grouping principles? Go ahead and answer. Pretty darn cinchy, if you ask me. Oh yeah, you know this one. All right, I'll give you another 10 seconds or so. Great. All right, you did great. The correct answer is, of course, C, feature analysis. I mean, we just talked about it, but you get a free question. There you go. Affordances, for your information, is something we will learn about next week when we discuss our final theoretical approach. Emergent properties, we will discuss on Tuesday. That's another theoretical approach. Don't be scared that you don't know these terms yet. You will know them very soon. And then Gestalt grouping principles, you do know, but detection of simple components really wasn't the emphasis there, right? We talked about, trying to recognize the kind of organizational wholes, W-H-O-L-E here, wholes, and in a lot of ways, the simple components were interchangeable. So yes, feature analysis is exactly what we've just been talking about. It is going through feature by feature and trying to recognize patterns by recognizing those features and then how those features might be combined into things like letters, and then the pattern is recognized ultimately by that final level of that unit. Okay, that's pretty cinchy if you ask me. Hopefully very straightforward for you. Any questions on anything before we continue? All right. I have to say this live transcription does a better job than Siri, which is right. Siri doesn't, although, it might be the microphone. Now I want to try Siri with that. Do you think I'd look stupid wearing a microphone all day as I use Siri? I use Siri a lot, like, to send text messages to my wife and stuff like that. I'm from the generation that my thumbs don't work as fast as yours. So my wife and I both do this. I notice a lot of people my age will use dictation to send text messages, and it doesn't work that well. But maybe if I wear a microphone around all day, I would look important, right? People who wear microphones are important. Great. Megan says it's cool. Thank you. Oh, wow. All right. All right. People are making money. I wish I could wear a microphone. All right, thank you. Oh, sometimes people don't think I'd ever look stupid. Yes, it looks stupid, but you were at the BBC. Mason, good. Ooh, throwing shade, as the kids say. All right. All right. Thank you for that. You've made me feel much more confident about wearing a microphone all day long. Okay, let's continue. All right, we're going to change gears here a little bit. Oh, right, I forgot this term here. Sorry. These are sometimes these units in the brain that detect features are called feature detectors very often. Okay, and they are still an important part of neurophysiology and theories of perception, as we'll discuss. Okay, that there are cells in the brain, or sometimes groups of cells in the brain that respond, that are active when very specific features are shown. That's all that is, right? It's like, trying to provide now the neural version, the nervous system's version of these little units that detect features. Here they're called, appropriately enough, feature detectors. Cool. Now we're going to switch gears a little bit, and we're going to go back into some philosophy. We'll come back to this stuff later on in the quarter. You'll see that, in fact, our next theory is going to do some really interesting modifications of that kind of tree diagram you saw on the last slide to kind of generate a new theory. But let's get a little philosophical again. And we're going to readdress this issue that we discussed a couple classes ago. The homunculus problem. Remember this problem. And here's the idea. Just to remind you that when we deal with something like representations, which we believe, most psychology, if not all of psychology, is comprised of, right? I mean, as we understand this, when you think of your, significant other, your parent, our ability to think about them, imagine now your mom, I don't know, leaving for work or something like that, grabbing whatever she does, or if she works at home, whatever, doing some type of work, we can manipulate that representation in our brains. We know that it is a representation. It's not, our moms aren't actually in our brains, even though sometimes it feels like that. It is a representation of our parent. And that's not just true of that, specific scenario. It's true of every psychological process we can talk about, right? Psychology involves, in some ways, the manipulation of representations, whether it's a manipulation to imagine, what our, a mental image of our parents are doing, or, if we're talking about representations of features in the letter R, there's a manipulation of the symbols in some ways to determine what the final image is. So the actual process of recognizing something on the outside does involve representations somewhere in the mind and somewhere in the brain. So that's what we were talking about, right? So every theory we've discussed so far, and most of the theories we'll discuss overall, do involve representations of things in the world in the process that we're going through, right? So if that's the case, then we need something to, kind of interpret the representations, right? In our original portrayal of this homunculus problem, we talked about how the Greeks thought there had to be something that interpreted a representation. And here, we're just kind of portraying the representation as something on the back of the eye. It is inverted and distorted, but, we can say that there is a representation that we're now starting the process off with. Right, and maybe we'll combine it with other representations. We have a representation in our minds of linear perspective, for example, that can tell us something about how far something might be away, its distance, which then would allow us to determine the size of this or something. That's also a representation, though, right? We can now manipulate these representations together to try to come up with an idea of what's really out in the world. Okay. So in order to do that, though, we need something to interpret what the representation is, right? So there's our little interpreter, and remember we went through this, and that's, I think, as small as I can make it right there, but the idea is that it goes on infinitely. But what we would need to do is solve this problem, right? So philosophers have been concerned about this for forever, since the 80s, and maybe even earlier than that. And here's an example: a philosopher named Daniel Dennett, and you're not responsible for remembering that name. You might see it, but I'll associate it with concepts. Daniel Dennett in 1980 wrote a paper about representations and all of psychology and the homunculus problem. Well, let's remember that the homunculus problem is the issue that by kind of just pushing the interpreter deeper into the system, in some ways you're not solving the problem, right? You're not kind of kind of creating a viable solution then. And what Dennett said, this is radical, but I think very provocative. He said, well, any science that is going to kind of assume that is based on representation, any science based on representations, okay, is going to need an interpreter for those representations somehow. And the interpreter of representations leads to this, kind of infinite regress. Remember that term? Just like never really solving the problem, because we're just saying, oh, how is it interpreted? There's an interpreter there. Okay. How is that interpreter being interpreted? Oh, another interpreter. It's not a real solution. It leads to this infinite kind of regress, this kind of circular sort of explanation that's just not satisfying. And then it said, so any theory that is dependent on representations being interpreted is not viable. Any science that's dependent on representations being interpreted is not viable. And psychology is dependent on representation. It's dependent on mental representation. So Dennett says, psychology is not a viable science. Okay. Class dismissed, right? We're done. Change your major, quick. Is there a way of solving this? And this is how he starts this very provocative paper. And I think it's a really important thing to consider, right? Any science that's based on mental representation, assuming that there are mental representations, and that all of psychology is, right, is doomed to failure, because these representations need to be interpreted somehow. And, historically, theories that involve interpretations of representations fall prey to this homunculus problem. And we know that's not really a solution, right? Just pushing the problem deeper and saying, oh, we'll let another interpreter, or maybe we'll tell the biologists they've got to worry about how that interpreter is built. And so Dennett was very concerned about the future of psychology. Can you do a legitimate science of mental representation, which is what psychology is in a way? And fortunately, at the time, he came up with a solution. He said that the only solution that is at all viable in this context is computation. By thinking of the brain and the mind as a computational system, what it allows us to do is to reinterpret the homunculus, okay, this interpreter, as being a system that is basically spread out among systems that are very, very stupid, that don't have the same sort of sophistication as the process we're trying to explain. Right. So that's really kind of a way of thinking of the homunculus problem. Right. So why is it a problem? Well, how is this interpreted, this stimulus that comes in here? Right. We say, well, there's an interpreter in here. The problem now is that we're not really explaining anything, because now this interpreter has the same kind of, skill that we're trying to explain, and we're not explaining this. Right? It has the same, I'm using the term a little loosely here. It has the same type of intelligence that we're trying to explain. So yeah, that big head, Rosenblum's bald head, has the ability somehow to perceive, to at least some degree, what's out in the world. Okay, through many steps and all that's not direct, right? We know, but it's going to be able to determine what's out in the world, right? That's an act of intelligence. But then, if we just say, oh, there's an interpreter back there that's able to do that, this little interpreter has the same act of intelligence as the thing we're trying to explain, and so it's not explaining it at all. That's the infinite regress, right? But what Dennett is suggesting, that if we think of the interpreter as being made up of little tiny on-off switches, which is what the computational approach is going to do, we're basically dispersing this intelligent act of being able to recognize something. So that's what I mean by here. It's dispersing the intelligence. We're trying to explain a, quote, intelligent process of being able to perceive what's in the world. And rather than saying there's an interpreter inside that's going to be able to interpret the representation, which is also an intelligent process that's pretty much as intelligent as the thing out there, then it's going to say that thing we're calling the interpreter is not really an interpreter. What it is it's a huge process. And the only thing it's composed of are on, off, yes, no, 0 and 1 states, right? Okay, it's actually even more useful than that, Dennett's saying, because what we can think of as the interpreter is at first at a kind of more global level, kind of like little boxes in a flow chart. Okay, so we've talked about this sort of thing before when we were discussing different ways of thinking of our theories of perception, that the information comes in and then kind of goes through these different steps. It goes through the receptor organ, then this sensation, and then inference or organization or whatever. We've seen that. This is another type of flow chart, and actually this isn't it is an example of a flow chart. This one has to do with how a system might be able to determine whether a fire alarm has been sounding or something like that. So it is relevant to perception, certainly, but it's one on sound in this case. And this is so we could portray a perceptual process in this way, where we look at kind of more simple components of the process of perception. So a fire alarm sounds. Does a system, maybe does the ear detect a sound? If no, okay, oh, what does it say? Get a hearing aid. Okay, fine. Maybe that's not a great one. But if yes, then it says identify, is it detect a sound? And if it is a fire alarm, then it goes through a process. If it isn't a fire alarm, then don't worry about it, right? So this could be a portrayal of a perceptual process. And so what we're doing here, at least in an initial kind of computational reduction of the interpretation, is breaking the interpretation down into smaller pieces, right? Smaller pieces. We could talk about this in terms of the Pons illusion. Maybe that will be more intuitive. And I see people are asking questions in the chat. I'll get to those in a second, I absolutely promise. But let's think about it as the Pons illusion. And I don't have that on this slide, but you remember the Pons illusion. And we talked about this unconscious inference process, where the first part was kind of measuring the two horizontal lines. Okay, so we could, kind of make a little flow chart for that. Are the lines equal? Yes or no? If it is equal, go to this box here. If it's unequal, go to this box here. Okay, if it's equal, is there information that they might be located at a different distance? Is there linear perspective? Yes or no? Is there linear perspective? No, no linear perspective, no information for distance. Then in fact, they might, we go to this box and they might be, at the same size, right? But if there is information for linear perspective, then do this. So basically, you can do one of these flow charts for any perceptual process. This is kind of like, a way of portraying that rule system that we've been discussing as, something a Turing machine can actually support, right? And so already we've taken the idea of an interpreter inside the system and have broken it down into something that's much less intelligent here, right? These are now kind of stupid yes, no decisions, right? Are they the same size? Yes, no. Is there information for them being at different distances? Is linear perspective present? Yes, no. You get the idea? These are very dumb little decisions that need to be made, right? And even so, it's basically now our interpreter becomes a collection of very stupid little homunculi where they're just making yes, no decisions. And even dumber than that, is that any representation of these states, the representation of a horizontal line of a given distance or of a given size on the back of the eye, okay? Those themselves are comprised of stupid little switches, binary switches. So this whole interpreter now is really just made up of the dumbest possible homunculi you could ever imagine. And so it's not like, okay, so these are just yes, no states, just to remind you, A's and B's, zeros and ones, it doesn't make a difference. These strings of yes, no states, all right, are going to be what's representing, any pieces of the input, any pieces of a memory we might have of linear perspective meaning distance or something like that, as well as any of these little decisions here. And so we're dealing, by making this a computational process with, a dispersion of this intelligent interpreter into the dumbest possible things, okay? In other words, we're really kind of not dealing with the problem of having to explain an interpreter that has the same intelligent act as the perceiver, him or herself, okay? Right? And so this could solve the problem, says Dennett. We're not kind of, just pushing the intelligence back. We're taking what could be an intelligent act, but dispersing it over, these units or these decisions that are so dumb that really it's not really kind of pushing the problem. It's not really kind of putting off the explanation, okay? And of course, if this can be in the nervous system itself, if these on-off switches could be, supported by the on-off states of nerve cells, then maybe we're solving a homunculus problem, right? This might, in fact, solve how we're able to perceive without kind of running into the homunculus problem. Does this solve the infinite regress that the homunculus problem posed for us before, right? Kind of a provocative idea. Now, people are pretty impressed by this, right? It's like, well, okay, now maybe we don't need to worry about the sort of homunculus problem. Maybe we don't have to worry about the general problem in psychology of having to kind of explain an interpreter that's, kind of tasked with the same sort of perceptual skill that we're trying to explain by the person who is perceiving. Because what we're doing is we're showing, well, it's based on this internal interpreter is based on things that are not, don't have the same requirements for their act of intelligence. Instead, it's just dispersed and they're dumb units, and these are much easier to explain. And in fact, they're easy to explain in the brain because, we're talking about cells being on and off. There you go, right? Possibly. Maybe some of you are thinking about this. Like, there is some intelligence here that goes beyond the just simple yes-no switches, because somehow those yes-no switches, those strings of on and offs, A's and B's, zeros and ones, have to get organized, right? So there is somehow, in order for these strings to be useful, okay, they have to be organized in a useful way. They have to be, the units themselves can be as dumb as anything, but what makes this a useful, sort of mechanism is that these dumb units have to be organized. They have to be strung. They have to be ordered in a way that then makes them useful. And where does that come from? Where does this design of yes-no switches come from? And you could say, well, we'll say it comes from the evolution of the system, that they get ordered. These kind of yes-no states, these neural states are something that evolution kind of designed, right? And so really what we'd be doing here is giving the job of explaining, where the intelligence is in this system to the biologist, the evolutionary biologist, perhaps, or something like that. And the question is, are we comfortable doing that? So maybe then it helps us solve the homunculus problem, but maybe we still got a piece of it we've got to deal with somehow, because yeah, the units can be as dumb as anything, and that's a relief. We don't have to explain the same intelligence that we're trying to, same intelligence of our interpreter that we're trying to explain of the perceiver outside, right? But, those units only become effective by being organized, by being ordered in a smart way. And somehow that intelligence has to come from somewhere. Question is where? Evolution, okay? Somewhere in the deep neurophysiology. Okay? So there's some people that feel that might not quite solve the homunculus problem in a way. Okay, cool. All right, let's continue, because this is so much fun talking about the philosophy. Actually, let me take a quick couple of chats here, see if people have any questions. Someone's going to change their major to RN because of me? Oh no, I hope we didn't scare you off. Maybe it was my video of the close-up of my face. I'm sorry if I did that. So now is, okay, so Kelly asks, so now is it explained by all or nothing method? Either is it true or not computationally? So I think what you're asking is this the only solution to the homunculus problem? And you'll see it's not, Kelly, if that's what you're asking. And you'll see that some folks believe that might not be a solution, as we just discussed. What about babies, Brianna asked, right? Okay, so is there, so potentially nature could give some shaping to the organization of the on-off states, some shaping to the kind of computational states that solves the problem, but we've learned, right? So there has to be some ability to organize these on-off states. But remember that the Turing machine can do this, right? In some ways, the Turing machine can say, if this input exists, and you see that then kind of feeds into a new string of zeros and ones. If that new string of zeros and ones is in fact detected by the tape machine, then it can go ahead and write a new series of 0 and 1. So Turing and folks that are thinking computational is the way to go for thinking of the mind, they do incorporate ideas on how learning might occur and how new strings might be written, but there still needs to be some kind of fundamental kind of understanding of how to interpret those inputs in order to write the new string. So it's a very good question. Cool. All right. Let's continue then talking about the philosophy stuff, and then we'll go ahead and do our question, our final test question for today. We're going to talk about something you did talk about yesterday. And this is the question about whether formal systems know. And I'm just going to review, I'm sure, what they discussed yesterday in discussion, just a tiny bit, just to kind of get us into this question. And it has to do with the Turing test, right? So I know we did discuss this yesterday. What is that? Oh, there's Taylor Swift. Why is she in there? Oh, I know why. Because yeah, like many of you, I'm a big Taylor Swift fan, right? Love her music. Wish I was part of her, what is it called? Her clique? No, her posse. Okay, along with all those other famous people. So far, I haven't heard from her. I don't think I'm going to be invited, but if she does, you'll have to find another perception teacher, because I'll be hanging out with her posse. But I'll often go onto the Taylor Swift website, and I will chat with folks on the website. And one day I was chatting about Taylor with somebody else, and this person, whoever they were, said, asked me about my favorite Taylor Swift song. It's that song Next. Is that the name of it? Or, where she's talking about, her next significant other, or whatever that name of that song is. The person I was talking to said, oh my gosh, that's my favorite song too. And I said, what's your favorite performance? Have you seen her in concert? All this stuff. We go back and forth. And after a while, I realized that I'm not talking to somebody. I'm talking to a Taylor bot that has in fact been created by Taylor Swift's clever web designer to keep people like me, a Swiftie, engaged in the website. Okay. And it's like, oh my gosh, I was fooled into thinking here I was talking to another Swiftie. But it wasn't. It was a synthetic Swiftie that was designed. I'm sure there are synthetic Swifties that was designed to make me think that I was talking to another real live human fan. Okay. Now, after this happened to me, after pretend it happened to me, I sat back and thought, my gosh, I just interacted with this synthetic Swiftie, and I thought it understood what I was saying. Boy, it really seemed like it did. The question is, did it? Did it know what I was asking it? Did it know the trivia it was telling me about Taylor, right? Typically, we'd say no, right? I mean, intuitively, we'd say, no, it's a machine. It doesn't understand anything, your toaster oven doesn't understand when it's time to stop, toasting the toast. It's a machine. It doesn't understand that. Your thermostat in your room doesn't understand when it's time to turn off the, air conditioning. I mean, it does it, but it doesn't understand that it's time to do it. We don't say these machines have an understanding, right? But the question is, what allows us to believe we have an understanding? Why do we think, the Swifties truly understand the subtleties of Taylor's various performances and what she's trying to, who she's writing her songs about, all of her various significant others? What allows me to think that Taylor has an understanding of her significant others, for that matter? What is it in Taylor that we believe supports her true understanding of things in the world, where the virtual Taylor, the synthetic Swiftie, doesn't understand these things? Is it just because she's made up of a biological set of tissues, and the computer that's pretending it's a Swiftie does not? Okay, what is it that does this? Well, you know the story, right? There are ways of possibly testing this. I mean, I think my virtual Swiftie, my synthetic Swiftie, might have passed the Turing test, right? Because I thought I was, in fact, interacting with a real Swiftie, but I wasn't. Okay, so it passes the Turing test, right? And you probably learned yesterday about some of the original Turing test devices, the Rogerian therapists. Now, you might be a fan of Dr. Phil. I don't know. Is Dr. Phil still on? Maybe you don't even know who Dr. Phil is. Oh, Dr. Phil was a TV psychologist who would solve people's problems, on TV. Some of us were rather worried about his techniques, but still, he was very popular. And Dr. Phil would very often use a technique where he would reflect back to people what they said. And this is a well-known technique, and it actually can be very effective. I'm throwing shade at Dr. Phil here, but the technique called Rogerian therapy can be very effective, in all seriousness, in crisis counseling. My son, at one point, my older son, was training to be a crisis counselor, one of those phone counselors. And that's what they teach, pretty much, which is a type of therapy that basically just rephrases what the patient says, and kind of shows that the therapist is listening. And it's a very easy thing to actually program into a computer. The client says, I'm upset about my significant other, and the Rogerian therapist would say, okay, it sounds like that your significant other is upsetting you. I mean, it's basically just a rephrasing of what's just said. And that's a very simple thing to do in a computer. And in the beginning, people would say, oh my gosh, it seems like I'm really interacting with a therapist, not a computer. But, it doesn't take long for that to kind of fall apart in the old versions. But now you know that there are new versions that are much more successful, right? But even if we don't want to say that, there's been a computer that's been designed to really, really fool us into thinking that we're interacting, during a conversation with a person and not a machine. So, maybe you played with that a little bit in your discussion sections yesterday. These kind of competitions where programmers design programs that, in fact, try to pass the Turing test, even if we're not quite there yet. I think we're getting close with the conversational robots, but even if we're not quite there yet, there are certainly instances where we interact with machines where we approach them as if they have some human characteristics. So, for example, Watson on Jeopardy. Now, this is many years ago now. I'm not sure you've ever seen clips of this, but it's worth seeing. So this is, Jeopardy, of course, and what they did in one part of the season, I can't remember how many years ago it was it 10 to 15 years ago? They actually had a computer as one of the contestants, and then they brought Ken Jennings in and other champions, past champions in to compete against this computer. There was somebody in the back, I guess, typing in the questions to Watson, this IBM supercomputer. And Watson did really well. Watson won a couple of rounds. There were very few instances where Watson kind of showed it was a computer. But if you ask Ken Jennings there, how you approached competing against Watson, the computer, he would say, oh, for all intents and purposes, I competed against Watson as if it was a human player. Okay. Every once in a while, Ken said, I realized that it would make a kind of quirky mistake that maybe a human wouldn't make, but for the most part, 95% of the time, I was, trying to compete against Watson as if I was competing against another champion, right? Certainly, and there's lots of other examples of this. So, Deep Blue, if you're playing, I mean, probably you experience this sort of thing, probably to some degree, I imagine, depending on how much you play online computer games. You could certainly be fooled into thinking you were interacting, in a first-person shooter game or something like that. You thought you were interacting with another person, but you were actually interacting with a computer-based player or something like that. So there are many examples where, yes, maybe we're not completely fooled in terms of being able to ask any question that we're interacting with a person versus a computer, but there are certainly interactions we have that, for all intents and purposes, we are playing against a computer as if it's a person and has goals and wants to win and means to beat us, wants to beat us in the game, right? That's certainly how Ken Jennings would play against Watson. Yeah, I felt it wanted to win. Okay, it's a computer, it's a machine. We don't think of it as having feelings. We don't think of it as having, a desire to win, to have the intent to beat me as I'm playing against it, right? But that is how, functionally we're playing, that it wants to win, that it wants to beat me, right? So in some ways, yeah, computers have passed the Turing test, just maybe not as a conversationalist, but that's not the only way to pass the Turing test. Cool. So what do we do here? Do we now say that computers have understanding? Does Watson have understanding? And if Watson doesn't have understanding, what allows us to have understanding that's different? What is it in us that allows us to have understanding that doesn't allow Watson to have an understanding of the Jeopardy questions it's getting? Well, here's what philosophers have said about this. Let's talk about what a computer is really, really doing. And they've come up with a scenario, and I don't know if, I don't think I asked the TAs to discuss this, but maybe they did. They're certainly allowed to talk about whatever they want, but either way, I'm going to go through this idea. of a scenario that was posed by a philosopher in the early 80s. In fact, it was a philosopher that had something to say about Dennett's idea of computation solving the homunculus problem. Searle says, let's imagine, here I'm going to give you the name, there it is, Searle, and I'm going to talk about the Chinese room example. Searle in 1980 says, Dennett maybe in principle could solve the homunculus problem, but we cannot discuss computation as the only thing that underlies human perception or human psychology. Because computers, if you think about it, really don't understand anything. Let's discuss what a computer is doing. A computer is manipulating symbols, right? That's all it's doing. And those symbols, as we know, it doesn't really know what those symbols stand for out in the world. Okay, let me give you a scenario that might help you understand this. Imagine myself in a room, okay? And I'm in a room. Do I have a picture of this? There I am. Yeah, okay, there I am in a room. I have a dog to keep me company, and I'm wearing shorts that keep me nice and comfortable. And here's what happens. I'm in this room, and there's a door to the room, but the door stays closed. But underneath the door, somebody from the outside is slipping in combinations of Chinese symbols, okay? Like these. Actually, I hope those are Chinese symbols. I don't know them. I don't know. I wouldn't know a Chinese symbol from a fake Chinese symbol. But here come these symbols. They slide under the door, and sometimes there's just 2, sometimes there's 6. You know, they come in sheets of you know, white paper like this. Symbols come in sheets of white paper like this. Sometimes strings, multiple ones. And my job is to take the sheets of Chinese symbols, go to a book I have, this big book I have somewhere in the room, look up what I look up and try to find the symbols in the book, and based on the strings of symbols I see, take a big stack of Chinese symbols I also have in the room and find certain strings of symbols and pass them outside to whoever just passed in the strings of symbols. So basically, here come the strings of symbols. I don't know what they are, but I have a book I can look up that allows me to look up the symbols, and then all it's going to tell me is what symbols I should now pass out underneath the door to whatever just passed in the symbols from the outside. Okay. I don't know what the symbols mean. I don't know if there's anything to do with language in these symbols. I don't know if, you know, I don't know if they're Chinese or not. I just have instructions on what to do once I get these symbols, which is to pass out a set of other symbols underneath the door to whatever's outside. Cool. You're outside though, and you have an understanding of Chinese, and you are asking me questions in Chinese, like, what's it like in there? Or, you know, am I comfortable in there in Chinese? Or am I lonely? Am I lonely? Here come the strings of symbols. Am I lonely? And all of a sudden you wait a couple of minutes, and then all of a sudden here comes this new string, and the string says, no, I'm not lonely. I have my little doggy here to keep me company. And you think, whatever's in there understands Chinese, but I don't. I'm just manipulating symbols. Okay. Oh boy, I realize I have to quickly do a test question. Oh, I'm having so much fun. Okay, here's your test question. I'm going to give it to you. So you have it, and then we will talk about it. Okay. Go ahead, just answer. You got 1 minute. The computational approach might be able to solve the homunculus problem through what? Unambiguous proximal stimulation, which you don't know about yet. Laws of association, which you do know about. Can it solve it through that? Emergent properties, which you'll learn about next class. Or D, dispersion of intelligence into binary decisions. Okay, I'll give you about 30, oh no, not 30. I'll give you 10 seconds, and then I'm going to give you the answer. We'll have to talk about this one at the beginning of next class. I'm just getting distracted on all this fun stuff to talk about, sorry. But the correct answer is, in fact, most of you got this. Absolutely. D, take a picture. We will talk about it next class. Have a good weekend, everybody.